Okay, hello and welcome everyone to the next event in our webinar series, a presentation by guest speaker Wim Bogaerts, professor in the Photonics Research Group at Ghent University and the IMEC Nanotechnology Research Center in Belgium. My name is David Hagen and I will be moderating today's talk. So it's a bit of background. Wim Bogaerts completed his PhD in 2004, pioneering the use of industrial CMOS fabrication tools to build photonic circuits. Between 2000 and 2010, he was the driver behind the buildup of IMEC's technology, silicon photonics technology. In parallel, he started developing design automation tools to implement complex silicon photonic circuits. In 2014, he co-founded Lucida Photonics, bringing the design tool Ipkiss to the market. In 2016, he won a research grant from the European Research Council, and since then, he's again full-time at Ghent University-IMEC, focusing on the challenges for large-scale photonic circuits and the new field of programmable photonics. Wim Bogaerts is also an IEEE and Optical Fellow and senior member of SPIE. It's always a fun one. Throughout this talk, please feel free to submit any questions you have using the Q&A tool. Vim will be answering any questions at the end. So without any further ado, I'd like to pass the talk off to Vim.
Thank you, David. And thank you, everyone, for joining this webinar. So today I'm going to give a bit of an overview of how we can use programmable photonic integrated circuits for the purpose of microwave and optical signal processing. And there's quite a lot in this title, so I'm going to use the title itself to kind of structure my presentation a little bit. So let's break it down into its components. If we're talking about photonic integrated circuits, for people who are not familiar with that topic, I'm going to introduce that a little bit. Circulation of light on the surface of a chip. But there's still different ways to do that. If we're talking about signal processing, well, it means that you basically have signals and you're going to transform these signals or you're going to extract information from it. If we're talking about microwave and optical, these are essentially different ranges of the electromagnetic spectrum, which today are used for a variety of applications and useful. And then if we're talking about programmable systems, well, that basically means systems that you can, or where the functionality is defined using software. So let's break this down and let's go through all of these one by one. And let's start with the bottom one. If we're talking about signal processing, there's different gradations of what you can consider to be a signal processor. It can but it does no interpretation of what the meaning is, of what meaning is encoded inside the signal. At a slightly more complex level, you can take a signal, but then you try to identify some meaning. Like, for instance, you figure out whether the signal at a given time is a 1 or a 0. And one level higher up, you can say we have computing, where you take the information from a signal or from multiple signals, and you perform some operations on that information, and then send that out again into some other signal. Now, the classical way today, or the most common way to do signal processing today is probably digital signal processing, which is actually, if you think about it, a very roundabout way to transform signals. You take a signal in, you digitize it, you discretize it, you use digital operations to filter or to do convolutions or other processing operations on the signal, and then you send the signal out again through the analog converter, putting it on some carrier wave to go to the next stage. Now, this is a highly successful technique, and the advantage is that it's also very numerically correct. Digital operations are very exact, but on the other hand, you're doing quite a lot of work and very inefficient operations to do tasks that might be done much easier. And the converse or the opposite of digital signal processing is, of course, doing the signal processing in the analog domain. And if we look at one particular type of operation that is quite common in signal processing, and that is filtering, that's actually a technique that has been well known to be possible to do in analog domain, even before it was done in the digital domain. Most signal function or most filter functions can be realized by just taking a signal, delaying it over multiple delay lines, and then combining those signals again, essentially performing an interference operation on the waveform of the signal. And if you do that properly, you can do equalization, you can do bandpass filtering, low pass, high pass filtering, etc. Now, so that's basically the type of signal processing that we might consider to do in the optical domain as well. And we'll come back to that in a minute. Now, talking about the wavelength domains or microwave domains, the signal processing that I talked about before can be done, it's kind of agnostic to which kind of waves you're trying to process, whether it's acoustic waves or microwaves or optical waves. So it's not a surprise that kind of we want to apply these capabilities to microwaves and optical. After all, they're both just different parts of the electromagnetic spectrum, be it quite widely separated parts. So in the microwave, we're talking about basically, if you push it hard, everything below 1 terahertz, while the optical domain starts really to become like what we know as optics from 50 terahertz, sorry, and beyond. So there's a big gap in terms of wavelength and frequencies, and therefore also a big gap in the techniques that we use to manipulate these waves. In the microwave regime, we're typically using electronics. Transport is via metal cables, coax cables, or is through wireless transmission. While in the optical domain, we generate our light through lasers, we process it with optics, and the transport of optical signals is usually done through optical fibers, which typically do not contain any metal at all. So there's a very different mechanisms being used to manipulate these waves, even though fundamentally, at a fundamental level, they're both electromagnetic waves. So can we bridge the gap between microwaves and optics? And the answer is yes. And basically the field that does this is called microwave photonics. It's basically a technique to try and process microwave signals into the optical domain. And why would you want to do that? Because in the optical domain, you have an enormous amount of bandwidth available. A wideband signal in microwaves becomes a narrowband signal in the optical domain, and that simplifies certain processing operations a lot. And the second reason is that in the optical domain, you have the availability of low-loss optical fibers. It's very easy to transport a signal over a very long distance with very little loss, which is, in microwaves, not always easy to do. So the idea of microwave photonics is to take an optical laser line, an optical carrier frequency, you emit a single frequency laser, and you modulate a microwave signal onto that laser line, very much like you would modulate an FM radio signal to a carrier. This signal can be transported, but it can also be processed, like filtered in the optical domain, before being converted back to microwave domain using, for instance, a photodetector. And then you can send that to an antenna, for instance, for emitting. And you can reverse this whole process as well to do a microwave photonics link in the other direction. So the combination of photonics and microwaves, even though on first sight they're widely separated in frequencies, actually can bring a lot of benefits. Now, if we have our signals in the optical domain, how will we manipulate our signals in that regime? Well, there's a lot of ways to manipulate optical signals. First of all, you need to realize that a beam of light contains a lot of information. We can talk about the total power in the beam of light at any given point in time, the intensity profile, the phase profile. Each beam of light has a wavelength, it has a polarization, and you can, of course, modulate it over time to encode a signal. So you have both spatial and temporal information in your beams of light. And manipulating those can be done in a traditional way, using lenses, mirrors, polarizers, phase shifters, phase plates, etc. Now, this works for limited scale systems, but it's always very tricky to align everything. I know Thorlabs makes a lot of business out of, but in practice, at some point, this becomes quite unmanageable and unscalable. So if you want to do it in a more scalable way, you basically have to look at how they did it. You basically try to integrate everything on a chip. So if you can bring these together on the surface of a chip, you can basically make much more complex circuits or much more complex functions, because everything is also more stable on a single substrate. It makes everything more reliable. It shrinks everything down in size, reduces the power consumption. Basically, all the benefits that we encountered in electronic integrated circuits, we can apply to photonics. And that brings me actually to the next point. What are these photonic integrated circuits? Now, there's a very simple way to describe it. We manipulate light on a chip, but you can do light on a chip in very different ways. I mean, everyone has a smartphone which contains at least one camera, typically more than one camera. That's manipulating light on a chip. You have LEDs, that's emitting light on a chip. If you have an iPhone, you have a Face ID recognition, which contains an array of lasers on a chip, pixels. That's also light on a chip. But that's not the type of chips that I want to talk about today. Today, I'm talking about photonic integrated circuits, which are a very different type of photonic chip than the ones I show on the left. So what are they? Well, they're essentially a circuit. And that means that you try to make an abstraction of how the functionality of the device, of the chip, is being described. Instead of looking at the real optical physics that go on inside this chip, you try to make an abstraction of building blocks that transmit signals between the different elements on the circuit. And the elements of the circuit are not transistors and resistors and diodes, but are lasers that emit light, modulators that modulate light, wavelength filters that separate different wavelength components in the spectrum, photodetectors that convert light back to electrical signals, and of course, interfaces to fibers that basically can send the light on and off the chip, for instance, to a different part of a larger system. Now, what are the typical components? I already mentioned them. So we need the light sources, we need to transport light, filter light, modulate light, and detect light. Now, the key thing is that you hook up all these components together with waveguides. And a waveguide is a very simple device. It's similar to an optical fiber. An optical fiber is a type of waveguide. But in this case, we want to make waveguides on the surface of a chip, which means we need to define some typically rectangular strip of high refractive index surrounded by lower refractive index. And the light is confined, it's bound to this high refractive index core in the middle. And if you design it properly, you can easily guide the light around the corner as long as you make your bend radius not too sharp or not too small. So a waveguide allows you to route light on a chip without losing it and basically without talking it to other waveguides. You can make additional functions on the chip, like for instance, a 3 dB splitter, so that it basically incoming light is split over 50-50 over two outputs. You can combine splitters and combiners into, for instance, an interferometer circuit. So in this case, we would have a coupling structure that splits the beam into two parts. Then, so you have two parts of the beam, and then you basically couple them again together. And depending on the different in length of these two arms, you can now control how much light goes into one output or in the other output. You can do that, for instance, by introducing a little bit of phase shift here at one of the arms, slowing down the light in one of the arms a little bit more than in the other arm, so you can control whether the two beams arrive in phase, giving constructive interference, or out of phase, giving destructive interference. And that allows you to determine how much light goes into each of the outputs. You can also do that to make a wavelength filter, to basically selectively send some wavelengths into one output and some wavelengths into the other output. And you do that by introducing a phase shift that is wavelength dependent, just by adding a little bit of delay with a path length difference of delta L. And if you add this delay, you will see that in function of wavelength, you get a kind of periodic response with high and lows depending on the wavelength of the light. You can also route waveguides in loops that gives you a resonator. If the wavelength fits inside the ring an entire number of times, you can basically have the ring absorb all the light and have it accumulate in the ring and dissipate in the ring, which will give rise to a very sharp dip in the transmission spectrum, which is also a very interesting component for a filter. And we'll come back to that later when we talk about programmable circuits. You can also use this filter with a second waveguide to filter out some light in an output. Now you can combine these Mach-Zehnders and these ring resonators into more complex filters. So using an optical circuit, a very simple optical circuit, we can take light coming in from an optical fiber, send it through a filter and send it back out to create an optical filter circuit and to, for instance, filter out the passband of light or to make or to separate the spectrum of light into different components. On top of these functions, like these filter functions, we have other sets of functions, which we call typically active functions. Filters are passive because they usually can be described by a linear transfer function, while active functions really do change the photons in the system. They either absorb it, they modulate the photons with the signal, or they generate photons or provide gain. And active functions typically include depend on the materials that you can include. For instance, if you want to emit light, you need a 3,5 semiconductor that has a band gap in the right area, like for instance indium phosphide, which you can then use to emit light at those wavelengths. If you want to do a modulator, you need an electro-optic material that responds to an external voltage and gives a change in optical properties, like for instance lithium niobate. Other materials include silicon, germanium, aluminum oxide, silicon nitride. There's a lot of different platforms today that can be used to make photonic integrated circuits. Now, which one to use depends on the applications, and the applications depend very much on the wavelength. So today, optical fiber communication is mostly datacom, telecom in the region between 1.3 and 1.6 micron. And you see that most of these platforms support that wavelength range. While other devices like medical devices or gas sensors require either long wavelength or short wavelength. And therefore, you have to find a wavelength platform that works best for you. Now, if we look at the waveguide platforms that are mostly in use today, then we see that today still a quite strong fraction of it is 3,5 semiconductors, represented here by indium phosphide, the green box, and gallium arsenide, the red box. However, we see that one color is growing much faster than everything else, and that's this blue color here at the bottom, which is silicon. Now, this is quite peculiar. Silicon as a material for optical circuits is not a natural material, as we will see in a minute, but it allows you to make use of the same infrastructure that is already there for making CMOS electronics. And that's a very appealing prospect. By using silicon, we can make high density photonic circuits in a CMOS fab. So we don't have to invest in new infrastructure to make these silicon photonic circuits. Now, what are the typical circuits that are most used today? They're essentially transmitters and receivers, the circuits needed for data communication. And in essence, these are very, very simple optical circuits. You need some laser to generate light. You need a modulator to encode a high-speed signal onto your optical laser line. You need to send it out to an optical fiber. And at the same time, you need an incoming signal coming back, and you need to be able to detect that signal. Now, that signal that is being detected is not necessarily high quality. And we might, for instance, need to perform some filtering function on such a signal. And that's where our idea of optical signal processing comes in. What if we now put a filter circuit inside that chip and start programming of how these circuits operate? Now, as circuits becoming more complex, we see that we are adding also more and more functionalities on the same chip. So we get circuits of not a few components, but tens of components, hundreds of components, and we're even going to circuits of thousands of components. And you can plot that kind of on a Moore's law scaling plot, so logarithmic scaling plot as function of time. And indeed, you see that today we're hitting the 10 to 100,000 building blocks per circuit, even though these are kind of hero experiments, but we're kind of on a path to growing to about 1 million components on a chip. Now, for that to really become productive, there's quite a bit of work that needs to be done. But it's nice to see that even with all the effort that's being put in, that we're slowly getting there. Now, before we dive into the main part of the presentation, let me discuss the last word in the title. That's programmable. That's actually quite easy to understand. We're all familiar with programmable devices. Everyone has tens or even hundreds of programmable devices in their house, in their life. Everyone is watching this on a computer or a phone. These are programmable devices. A lot of the functionality of those devices is determined by the software layer that is running in between the user and the device. Now, if we look a bit closer to hardware, do we know programmable hardware? Yes, then in electronics, I think the best example of programmable hardware is what we call an FPGA, or a field programmable gate array. This is essentially reconfigurable hardware of logical blocks that can be configured with a lookup table, and then connectivity that can be programmed so that these blocks can be wired together in an arbitrary way. Now, these FPGAs have been introduced in the late 1980s and early 90s and have become hugely successful. I mean, this is kind of the go-to building block if you want to fast, rapidly prototype a new idea in your for an application. Now, these concepts have also been tried to do analog signal processing in electronics, but with very, very mixed, well, actually little success. So trying to build an programmable analog circuit, run quickly into power consumption and also bandwidth. So there was a bit of a problem that electronics was fundamentally limited to really do analog signal processing in a programmable way that was very flexible. And that's where I would say programmable photonics comes in. Can we use photonics with its much wider bandwidth and its different set of building blocks to make analog optical functions, but that can still be digitally programmed, that have a high bandwidth so that we can use it to process microwaves, and that are hopefully as extremely successful as FPGAs. And we could call these photonic FPGAs, you could call them programmable photonics or reconfigurable photonics or photonic processors. In the end, it all boils down to the same thing, a photonic integrated circuit that can be reconfigured in software to perform different functions. Now, how do we go through this? Well, such a processor would basically need to be able to process optical signals, so it needs optical inputs and outputs, but it also needs to perform operations on microwave signals. So it needs a high-speed RF input and a high-speed RF output. Now, how to make such a processor? That's not necessarily a simple proposition. So that's where we come back to our full title and what we're going to cover now in the next half hour. Let's start just simply from our transceiver that we had before. So we have laser, modulator, and an outgoing signal, and an incoming signal, and a detector. Now, if we want to do some processing, like for instance, a filtering function or equalization on a signal, that's actually fairly easy. You put a filter, an optical filter circuit in the path of your light, for instance, at your receiver. And so any distortions that are being accumulated in the optical fiber could be compensated by this optical filter. Now, it becomes more interesting if we remove the fiber altogether. What we have now is an optical path on the chip, but it remains entirely for its entire function on the chip. So from the point of view of an outsider, this looks like an electrical chip because it gets a microwave signal in and a microwave signal out. Now, if we make now every function on this particular chip programmable so that you can tune the configuration of the modulator, that you can play with your modulation format, that you can play with your exact filter profile, you get a kind of an analog signal processor that can process microwave signals. And if you now also make it possible to bring in optical signals at different points in the flow, you have a chip that can process optical signals and microwave signals. We actually made this chip. This is the result of one of my students, Hong Deng, who designed and had this chip fabricated and then characterized it. And indeed, with this chip, he could demonstrate quite a lot of different functions. I'll just show a few. This is the package version, so it has both high-speed microwave connectors and optical connections, which at this point are not yet connected, so there's no fiber array yet. And everything is on a temperature-controlled substrate. So one example of what this chip can do, if you come in with some light from the outside, you can actually use a programmable filter to filter the light and to get a bandpass filter with different shapes. There's a Fano resonance filter, a ring filter, a multi-passband filter, etc. And the passband is tunable and can be entirely programmed using all the optical tuners on the chip. Likewise, you can use a similar filter to filter microwave signals. In this case, you modulate the signal on to the laser line, and you can do a bandpass filter, a low-pass filter, a high-pass filter. There's plenty of other possibilities to do with this circuit. You can do frequency doubling. You can make an optoelectronic oscillator. All the details are published in this archive paper that hopefully somewhere in the next months should also become published in a regular journal. You can, I mentioned that you could do an optoelectronic oscillator. So using this little chip as an engine in a larger system, like adding an amplifier, you can make a tunable oscillator that can generate frequencies between, in this case, 4 and 24 gigahertz. And this was only limited by our measurement equipment. So it can also run at higher frequencies. Now, this is just an example of a programmable chip that can already do quite a lot of functions, but it's still in a way limited. The flow of light only goes from left to right in this picture because it goes from the laser to the detector. It can handle only a single function or a single signal, one thing at a time. There's no programmable delays apart from the ring resonators that are in there. So it would be nice if we can do a little bit more. And this brings us actually to programmable photonics, as I would really define it. And even within that field, like more general purpose programmable photonics, there is quite a lot of different architectures. And let me start with the simplest one, which is called a forward-only mesh. The name says it itself. Forward-only means that the light propagates only in one direction, in this case from left to right. And what you have, it's a mesh of waveguides that are coupled together with what we call an optical gate, which controls the phase delay and the coupling between the waveguides. And with that way, you can basically mix your light from a set of inputs into a set of outputs in an arbitrary way. That results in what you could call an arbitrary linear transformation, which is really, really useful for a lot of applications. So what the optical gate itself does is essentially just mix the light. So you have a controlled coupling coefficient and delays one wave with respect to the other. So that is enough to make essentially any arbitrary linear transformation if you cascade these gates together. And the only components you need for that is some phase shifter and a tunable coupler. So it's a very, very simple basis set of building blocks that you need. And it can be even simpler because a tunable coupler can be made in the form of a Mach-Zehnder interferometer with just 2 phase shifters in there to control both the coupling and the control of the phase separately. So in essence, you only need a very good electro-optic phase shifter to make this work. And that's good because you can make very complex circuits with only a few building blocks. How this actually works can be easily illustrated if we take a gate like this. And in this case, I have a phase shifter and a tunable coupler separately. And assume that there is light coming in 2 inputs, but you have no idea what the relative amplitude and phase of the light is. Now imagine that we want to configure this gate that it couples all its light into output 2. This can be done without knowledge of the input signals by just using very simple feedback loops. We basically just need to detect the light in output 1 and try to minimize this. And we can do that by adjusting the phase in the phase shifter to make sure that the light in output 1 gets canceled out as much as possible. However, there's still a bit of light coming through, but now we can use the same detector to minimize the coupling or to adjust the coupling until both contributions completely cancel out in detector 1. And that way, without doing a computation, we've minimized the power in the detector 1 all the way to 0, which means that all the light has to end up in output 2. And the nice thing is that we can cascade such a circuit, a simple 2x2 circuit, to a much larger circuit to, for instance, minimize the power in output 1, then output 2, and then output 3, resulting in all the light going into output 4. Again, without having any prior knowledge about the optical distribution in the different inputs and their relative phase, and without having to do any pre-calculation of what the state of these individual gates need to be. Everything can be done quite easily with just an optimization routine, a local optimizer. Now, why would you use such a system? Well, this is an example from the Politecnico di Milano. They basically used this to make a set of antennas, optical antennas, that allow you to maximize the amount of power that goes from one building to the other in a free space optical link, even in the presence of turbulence. And because turbulence continuously changes the shape of the beam, you have to continuously adjust the receiver circuit to capture that beam. And that's done in this way. You basically have a set of lenses. They couple into a set of grating couplers that go onto the chip. And then you have all these yellow detectors here that automatically minimize their own power. And because when these detectors minimize their power, that means that all the light will go into the receiver detector at the end, the green detector at the end. And that works actually quite well. So this is the circuit that they used for that. Of course, the circuit needs quite a bit of electronic control. But then if you look at the results, the blue curve here on the left shows the situation where the control is on. And then if you switch off the control, you immediately start losing power and you get a lot more variation in your received power over time. And this is running over many, many seconds. So it's actually a fairly long time. This is another example of such a forward-only circuit. It has 26 inputs, 26 outputs. And it was developed for basically performing linear transformations. So not just optimizing the beam power, but to really perform kind of computations on light. How can you do that? Well, if you have input waves of light, you can represent those input waves as a set of complex numbers, the amplitude and the phase of each wave in each input. And the same we can do for the output. Now, if you start mixing all these waves together in this circuit in the middle, the circuit essentially performs a matrix vector multiplication in real time, in the time it takes for light to propagate from left to right through your circuit. Now, that's nice because these type of operations are super useful for quantum information processing, for pattern recognition, and also for neural networks. So there's a lot of publications and studies of these type of circuits to, for instance, make accelerators for matrix vector multiplications. However, the companies, the most high-profile companies that were working on this have actually now switched topic a bit towards interconnect fabrics. So they're no longer very heavily pursuing these concepts at the moment. But the quantum people, they don't really have much alternatives for this type of architecture. So companies like Quix and Xanadu and PsiQuantum are still heavily researching these kind of large-scale forward-only meshes for doing quantum information processing. Now, these forward-only meshes are already much more programmable than the first circuit I showed. But on the other hand, it only has passive components. Light only flows still in one direction. All the light paths are typically balanced, equal length. And also, you can't just choose whether a waveguide port is an input or an output. It's already defined up front. So we still would like something that's a little bit more general purpose than these. And for that, we go to the next concept, which is a recirculating mesh. So a forward mesh, like I said, it basically has a set of inputs and outputs, but there's no feedback. There's no wavelength filtering capabilities. If you want those functions, you need that in order to process time signals. You need that to do integration and differentiation operations. So if you really want to do signal processing, you need these functions like delays and optical feedback. So the solution is to basically go from this forward propagation to an all-to-all propagation, where every port becomes equivalent and you can couple light between every possible port and make that coupling also wavelength dependent. And the way to do that is using the type of meshes shown here, which we call recirculating meshes, which are essentially loops of waveguides that are also coupled together with the same type of optical gate that we used for the forward meshes. So in this case, you have a square mesh with 4 gates per loop, or a hexagonal mesh with 6 gates per loop, which allows you to route the light from any port to any other port. And that's actually quite easy to be done. You basically, there's something missing in the animations here on the platform, but okay, it's not a big issue. You can route your light basically by just switching the different couplers through different states, by switching them from bar to cross state. You can do that with multiple routes of light on the same chip. You can even split the light over multiple paths by just changing the state of such a gate into a partial coupling state. So you can make it work as a splitter. And that means that you can also make it work as a combiner. And now you can see that we've actually, by just configuring the states of these optical gates, we've configured a new circuit inside our circuit. We've made a Mach-Zehnder interferometer. And if you add a delay line to your Mach-Zehnder interferometer, you get the basis, the most simple basic component of a filter. Now you can do the same thing with the ring resonator that I introduced earlier. By programming the light to go into a loop, you can get a ring resonance and you get these sharp resonance dips. Now, the first demonstration of such a device was in 2017 by the Politecnica de Valencia. We recently made our own device last year that we now are operating. So it's a similar waveguide mesh. The components are a lot smaller now because we've evolved from the earlier technology demonstrated by Valencia. And we can now, when it's interfaced with the electronics, we can now demonstrate a lot of these optical functions. Like for instance, a ring resonator. So you see these sharp dips of the resonances. You can make a splitter tree, for instance, by separating the light over multiple paths. You can do programmable delays by just routing the light through a longer path through the chip. You can make filters that consist of multiple rings, so you can tune the bandpass characteristics of the filter. Or for instance, make an interleaver filter where you separate even and odd wavelength channels inside the spectrum. This is a more complex interleaver circuit. This is already quite complicated, using almost every element inside this small mesh, where we combine 4 ring resonators with a Mach-Zehnder interferometer. And this is a fully configurable 4-Torsder filter, so which can be used as a passband filter, as an interleaver, etc. This is another example, same configuration, where we basically tune the filter passband just by playing with all the coefficients of these different gates. Now, such a hexagonal mesh has some limitations. It still only gives you like a passive transmission or a coupling between all the input and output ports. And to make it really into a full signal processor, you need, of course, to have high-speed modulation, high-speed detection to interface with the microwave input and output signals. And then you might need some specialized functional blocks as well, or maybe even gain elements to complete the whole portfolio of building blocks that you want to use. Now, just briefly on what those building blocks actually are, especially the optical gates in the mesh. To make a good optical waveguide mesh, you need a very good optical gate. Just like in electronics, if you want to make really good circuits, you need really good transistors. So that those gates need to have low loss, short length, low power consumption, etc. Unfortunately, today, the building blocks that actually deliver on those promises, all of those promises do not exist. So the most common one used today is heaters, but they definitely don't have a low electrical power consumption. While most of the other blocks that are shown here, all the mechanisms, they have some other drawback, typically low optical loss or very difficult to integrate with the rest of the photonic platforms. On top of the individual gates, we need to make sure that we can make many of those on a chip and that we can also control them. So every optical element also needs its electrical control signal, which means we need a lot of electrical packaging, but also electrical drive circuits. We need to monitor what's going on the chip, and we need control algorithms to make everything work. So that means that for every phase shifter or every tunable coupler, we need some digital to analog converter, we need some digital control, and then we also need monitor detectors, readouts for the monitor detectors, and the control loops to control everything that's going on the chip. So when you make a chip programmable, it suddenly becomes a bit more complicated than just the optical functions. You need to be able to electrically and optically manage everything that's going on the chip. So that means that you need to look at close integration of photonics and electronics. And there's various ways going, but I think probably the most promising way in the near future is the fact that there's a lot of investments today in co-packaged optics, not for programmable photonics, but for high-speed optical interconnects. But the techniques that are being developed there could very well be a key enabler for enabling large-scale programmable photonic circuits as well. Now, what do you use for electronics today? Well, if you rely on lab equipment, then you're quickly going to break the bank. Today, if you buy lab equipment drivers circuits, that typically goes into hundreds of euros or dollars per channel. If you start building your own electronics with off-the-shelf components, you can bring that down to a few tens of dollars per channel. That's still a lot if you need hundreds or thousands of channels. So the next step is most likely a set of driver chips for electronics that you can use to drive a large number of photonic components on a chip. And hopefully that can bring us down to below one US dollar per channel. Now, I mostly was covering on the hardware. If you think about it, we need photonic hardware, we need electronic hardware, both analog and digital. But to make a programmable system work, you of course need a layer of software. Otherwise, it's not programmable. You need a kind of an operating system, and you need the routines that define the functionality of your photonic chip. So if we bring everything together, it would in hardware look a bit like this. So you have your light sources, your photonic chip, your RF inputs and outputs, and your optical inputs and outputs. But you also need a software layer that goes next to it that gives you the control, the configuration, and also for the people who want to create new functionality, a set of development and debug tools. And those software layers today, these concepts do not really exist outside of a few labs. So we have developed for our own chips, we have developed a software stack that combines a chip layout with circuit simulation and configuration and even hardware control. But that now needs to find its way into the hands of users. And at this point, this is very, very low level. It's kind of programming machine code for electronics. So there's a lot of need for higher level design capabilities. It also can change the way of how people design circuits. In the beginning, people designed geometries for their photonic circuits. Today, PDK-based circuit design is becoming the norm, where you take standard building blocks and wire them up together. But if you have a programmable photonic chip, you don't need to design a new chip. You basically design the connectivity and the states of all the devices inside your programmable photonic chip. So your chip becomes a program instead of a physical design. And to do that, you need good algorithms. You need a logical representation of your chip, for instance, in the form of a graph. You need routines that actually manipulate this graph, for instance, to do multi-routing or to perform splitter trees or filter functions. You need algorithms that can handle more complex functionality, like this particular algorithm developed at MIT, which basically can define an arbitrary filter response inside such a programmable photonic circuit. But most of these algorithms, most of these mechanisms are still today in a very, very embryonic state. So you can ask the question, like, is programmable photonics going to be useful? Today, probably not yet really there, but there is a lot of potential. Because today we're looking at photonic chips that are essentially just being pushed forward by data centers and AI. 99% of all the photonic chips today are transceivers, while that's basically saying that photonic chips, that electronic chips are only good for calculators. We know that electronic chips are used everywhere in all kinds of functions. With photonic chips today, that's a bit of a question. Where are all the other chip products, all the things that you can enable with photonic chips? And if you look at the predicted market, indeed, today it looks like most of the predicted market has to do some form of optical communication. So what can we actually do today with photonic chips? Well, there's plenty of possibilities, and most of those have been demonstrated in lab experiments already. You can, of course, do switching. You can do transceivers. We know that. But if you step outside the data centers, there's plenty of places where these transceivers can also be useful, like in microwave links for antennas, fiber to the home connections. And then beyond just optical communication, there's plenty of sensing applications where photonic chips are really, really useful. You can do readout for fiber Bragg sensors. You can do sensor readouts in a car. LiDAR is now getting a lot of traction to basically do for self-driving cars. You can do microwave processing, not just for communication, but for radar applications. And what happened here? In the biomedical world, there's all kinds of medical tests that actually can make a lot of use of optics, which can go from biosensors to, for instance, coherence tomography on your eye or on your teeth. So there's plenty of application domains where programmable photonics or photonics in general could be used. The question is how easy is it to access those markets? And if you just look today online and you try to figure out which products are there on the market that are not a transceiver, but still contain an optical chip, there's very few. And I think this is a fairly complete list. So it's not hundreds, it's not thousands, it's maybe a few tens. And that's something that needs to change. And the way to change this is to make it easier to develop photonic chips. So that means, on one hand, improving the first time right design capability so people can do faster iterations of new chips, but also make it possible to do rapid prototyping. And that's where I think programmable photonics can make a big difference in this rapid prototyping. Because instead of having to go through a year-long test cycle or design fabrication test cycle for a new custom chip, if you can do it in design and get first time right design, it already helps. But if you can do it in programmable hardware, just like the electronics people are used to with FPGAs, you can iterate in days. And you can actually fast track the development of a new product with orders of magnitude compared to taping out a custom chip for every iteration. And today this is very much needed because a product development in photonics can easily take 2 or 3 or 4 of these iteration cycles, which is very, very long. And that is holding back a lot of startup companies from really bringing a product to the market. So if you have a chip like this, which can basically route, split, filter light arbitrarily and do signal processing, you can speed up your developments a lot. But on the other hand, just like with FPGAs are typically larger chips than ASICs. They have higher power consumption. So same here, light has to go through more elements, higher loss. So it's not necessarily better in performance than an ASIC. So there's always going to be trade-offs, whether to use the flexibility of a programmable chip or the maximum performance that you can get with a custom design. But in any case, it has an economic benefit, because if you can make use of a programmable chip, you can save a lot on your development cost. If you have to do your own chip, basically all the costs for the electronics and the photonics is yours to bear. And okay, if you sell enough products, then you can recover that, but still, it's a very expensive upfront investment. If you can do it based on a programmable photonic chip, you basically share the cost of the programmable photonic chips and the electronics with a lot of other customers, just like with FPGAs. And FPGAs can be sourced pretty cheaply. If you can do the same with photonics, you can bring down the cost and the economics of photonic chips down a lot. Now, probably, and I'm almost at the end here of my presentation, it doesn't just give you a lower development cost and a shorter time to market if you could use a general purpose programmable photonic chip. It also gives you the kind of upgradability and reusability and longer lifetime that we today have learned to expect from our electronics. Getting a firmware update for your devices is nothing new, is nothing strange. But you also create a programming interface to your photonics that can be used by a much larger group of people. The moment you wrap a technology in software, you suddenly have 10 times the number of people that can actually use the technology. And the innovation potential there, I think, is totally unrecognized. So having a larger community basically creates the possibility for new photonic applications with ideas that we haven't even thought of today. So with that, I would like to summarize, give a quick summary. Oh, this QR code is the wrong QR code, but the slide deck will be made available. Now, programmable photonic chips, they're not yet a reality in the sense that you can buy them today. There have been proof of concepts. It shows promising for signal processing and for a variety of applications, but we're still in the pipeline of getting these chips to a level that we get satisfactory performance. However, the number of applications seems like endless. And given the fact that programmable photonics might shorten the development time for new applications, could really be a benefit and an enabler for the entire ecosystem. Now, if you are interested in trying out some programmable photonics, the chip that I showed earlier that we have realized, we actually wrote an interface to it online. If you want to make access to that, go to programmablephotonics.eu and just register. The chip is not online 24/7 because at this point we still need to attach it to a lab equipment for external people to use it. But if you want to try it out, just use the contact form on the website and check us out and see if you can do something interesting with this chip. Last but not least, I would like to thank all the people who have contributed results to this work. Too many to name them all individually. And then last but not least, if you're interested in learning more about photonic integrated circuits in general, I'm teaching a full week design course in April. There's still a few spots, so if you're interested, just get in touch or check it out and enroll in this design course. And with that, I'll just go back to the summary slides, and if there's any questions, feel free to ask.
Okay, thank you very much, Bogaerts. Really appreciate that talk. This is always a super exciting topic to me, just programmable meshes in general. The math nerd in me gets really excited when anything graph theory comes along. So interested to see sort of where the software takes you in this. So there's already a lot of good questions. I'm going to get started with a few here. So this one might sort of evolve into a multi-part question. What is the ideal spot size and working distance to improve performance specifications? Now, I know that a lot of the slides that you've been showing have been grading coupled devices. I assume edge coupling is also either feasible or on the roadmap. Would you mind talking a little bit about that?
Yes, so whether you use an edge coupler or a grating coupler, that doesn't really matter too much. In this particular case, in most cases, you're going to use a fiber interface to your photonic chip. And ideally, from my point of view, as a circuit guy, I just want to use whatever fiber coupling component has been optimized by the fab. So if the fab can provide me with a really good fiber coupling device, I'm going to use that. I don't really want to concern myself with optimizing fiber interface because every foundry is doing that by themselves. So of course, yeah, the lower the insertion loss, the better.
Okay, so I'll spin that question a little bit into a more tailored question, which is if you were buying, let's say, single mode lensed fibers to get the best coupling possible, what sort of spot size might you be aiming for?
I don't even want to use lensed fibers. I would look for an optimized fiber coupling design on the chip rather than using custom, very expensive lensed fibers.
Good point. Yeah. Okay. So the next question here, this is more of a processing question. What are the feature sizes of the waveguides and arrays created, and what patterning methods are generally used?
Okay. The feature size of the waveguides is typically dependent on the technology platform that you're using, the material system, and more particular on the refractive index contrast of the material system. So if you're using silicon on insulator, it has a very high refractive index contrast. Your waveguides are typically on the order of 0.5 micron wide and a few hundred nanometers thick. While if you're using a silicon nitride or a 3.5 semiconductor process, your waveguides will become on the order of maybe 800 or a micron wide. So it depends on the refractive index contrast. In our case, in the particular chip that I showed, that was a chip based on silicon. The waveguides are 450 nanometer wide, and the individual building blocks. So the heaters are about 50 microns for tuning the elements. The splitters are also about 50 microns long. So they're fairly compact devices.
Okay, and to build on that, what is the minimum feature size that can be achieved by the IMEC process?
Oh, you want me now to comment on the IMEC process? The standard IMEC process that you typically can get through MPW fabrication, so multi-project wafers. The minimum feature size I think is 150 nanometers, but that depends on the type of feature. I personally try to stay within 180 nanometers for reliable design.
Fair enough. Okay, another question. So we have, feel free to keep submitting questions. I don't think we'll have time to get to all of them, but if we don't, we have your information and we can reach out. So the next question, please explain why PIC technology isn't widely used for optical neural networks and nonlinear activation problems.
Okay, so if you want to do a neural network, you basically need two functions. You need an all-to-all like programmable matrix, and these forward propagation meshes, the forward-only meshes, are actually very nice for that type of function. And then you need some indeed nonlinear activation function. You need some thresholding function in your neuron that before it sends off the signal to the next layer. And that's something where optics is not as good at. Optics is good at linear processing, but not very good at nonlinear processing. So why are these circuits not yet used a lot for neuromorphic processing? I think for a couple of reasons. First of all, the maturity of the technology is not where it should be for really widespread use. There are people using it, but it's mostly for research. And also because a neural network typically consists of many, many layers. So in that case, you would either have to regenerate the signal between the layers, because in the optical circuit you would loss. So you would need to regenerate the signal, or you would need to go back to electronics photonics between every layer. And then the cost of your conversions between the optical and the electronic domain actually eliminates a lot of the benefits that you would have from using photonics. photonics is nice if you can stay in the optical domain, but if you have to constantly go back and forth to the electronic domain, you rapidly lose the benefits of using light. So I think that's probably one of the reasons, and like the reason why companies like Light Matter and Light Intelligence they were one of the first to move into this field as a company. They moved out. I think they saw better opportunities for their technologies first, and also the engineering challenges to really scale this technology up, both in yield and in terms of circuit size, were probably quite impressive. And the timeline was probably not compatible with their business goals.
Right. Okay, so we're running out of time here. I think we've got time for maybe one more question. So I'm going to shamelessly split this into a two-parter and talk about speed real quick. So when I think of these sort of optical FPGAs, I think there's sort of two domains of speed to be thinking about. One is, when you put modulators and detectors on there, what are the bandwidths of those components? But also in terms of switching instructions using the integrated microheaters, what does that speed look like, especially when you undercut them for improved efficiency?
Yes. So if you use microheaters for like the programming the mesh, programming the configuration of the circuit, and especially if you want to make them efficient, you use undercut. The heaters become quite slow. So we're talking about 100 microsecond time scale for switching or reconfiguring every element on the chip. Now, there's nothing that dictates that you can only use heaters. So that was kind of my appeal to the community. If someone can come up with the perfect electro-optic phase shifter that is not just compact and efficient, but also fast, I would be very happy.
Okay, I'm not sure if we've lost Vim or not. I will send him a message. Oh, there you are. Okay, so unfortunately, that's all the time that we have for questions. Again, if we didn't reach your question, then we'll reach out to you. So I'd like to thank Wim Bogaerts for giving this wonderful talk. Again, very interesting presentation. And our next webinar will be on March 19th, presented by guest speaker Dawson Bonville from the Integrated Optical Systems Group at the University of Twente in Netherlands. He will provide an overview of the field of integrated photonics, then discuss the recent work on reactively sputtered passive and active aluminum oxide waveguide platform. You can register for this webinar by clicking the Register Now button below or on our website at www.thorlabs.com/webinars. Thank you very much for your attendance, and we hope to see you again.